Next section we're going to move into is fuel tank venting. And the venting system plays a couple key crucial roles in fuel. It's probably the least remembered system in there. But we have these tanks. The tanks are on transport aircraft. They're almost always a wet wing design. So there are no bladders or metal tanks inside. It's the actual wing structure itself that forms the tank. The skin of the wing is the tank, and it is a sealed structure. Okay. Uh, Small aircraft use bladders, oftentimes rubber bladders, but large aircraft, it is when you open the panels on the bottom. If you go over to our 727 and you look on the bottom of the wing, there are a bunch of panels. If you were to open those panels right now, especially the inboard ones, if you open that panel, fuel would come dumping out on you. There is nothing in there to contain it besides the wing body itself. Okay? And so what that means is, as that is a fixed volume, that space, and so as we put fuel in that wing, we need somewhere for the air to go. As we burn fuel out of the wing, as we take fuel out of the wing, we need air to come back in to take that place so we don't pull a vacuum. We don't want to crumple the wing like a tin can because we pulled a vacuum inside of it. And so that's where the venting system becomes critical. Now, where we want air to come in and out, we do not want fuel to leak out. And so there are provisions in the venting system to prevent that from happening. And there's a few different things we can use. You'll see there's various items on here, but things like check valves that allow, in this case, here air to come in. This is a vent. These vent line tubes up here to allow the air to come in as fuel is burned down here. There are relief valves, which are to allow air to go out if the pressure gets too high. You can see these vents, they didn't just draw them going up. These vent lines on this aircraft, for instance, they come off the tank. They actually go up the side of the fuselage between two of the windows and then come back down again before the vent comes off the fuel tank, goes up the side of the fuselage, makes a loop, and comes back down and out. And that way, when the plane rolls, the fuel can't get up and over that loop to leak out the vent, right? But there's various other ways to do that. And then this even has a scavenge ejector, so if fuel gets into the venting lines, the scavenge ejector puts a little bit of suction on it and helps. This is a low point. It'll actually pull the fuel out of the vent lines and shoot it back into the fuel tanks. So it can keep those venting lines clear. Okay. And then you can see an air scoop is where it opens to the outside. It's not a great drawing, but this right here does not open into the fuel tank. It actually opens to a scoop on the bottom of the wing, a NACA type scoop. We'll look at what those look like. So a simple form of venting of kind of leak protection is a float vent valve. So at the top, near the top of the tank, you'll have a tube or a pipe that goes from inside the tank to a vent port of some kind on the outside of the wing or the outside of the tank. And they incorporate a float of some kind where if the fuel level gets too high, it pushes up on that float and closes that vent. So if the fuel were to fill above the top of the vent, it's not going to come pouring out there. Now, you still need to have something to prevent that from overfilling. I mean, there's a point where you can only push so much fuel into a space before it's full and it's got to go somewhere. So there would be other provisions to kind of prevent that from happening. But hopefully, in addition to these floats, you're going to have some kind of a sensor. When we do fuel level sensing, there'll be some kind of a sensor, it's called a high level sensor, that would automatically shut any kind of fueling valves to prevent that tank from getting any more full than what it is at this point. Okay, so that's one type. You can see these arranged. So this is that same wing structure we saw earlier. You can see all those little flapper valves, those check valves. But on here now we've added some different vents. And so there are, in this case, these vent ports right here are connecting the various bays together to allow air to move through the different bays. Even if those bays are sealed or even if they, the only way is for fuel to move near the bottom. We have an air thing at the top. We have a pressure relief valve shown. So if the pressure gets too high, This valve, it can push this check valve off its seat and allow air out. It's kind of a last resort. There's also a float valve, float vent. This is near the top of the tank, and it vents into this outer area, which is the surge tank, which is normally a dry bay. But if fuel gets into it, if fuel is able to slosh in, or if it gets into the different venting lines, it hopefully is going to stay, just a little bit that's at the bottom, and it can drain back down into the rest of the wing, and it allows air in and out. And then there's an air scoop, some air ducting that's attached to those surge tanks that are at the outside wingtips. So the surge tank, when I talked about different tanks earlier, the collector tanks in the middle where the fuel live, the surge tanks out at the wingtips are where the venting systems typically all tie into. And it's essentially a tank that's normally dry, but it can contain excess fuel or spillover fuel to prevent that from going out through the different vents on the fuel system, on the fuel tanks. So rather than, for a lot of tanks, a simple kind of schematic of it is if you have your main tank, and this normally has fuel in it, you can think of a surge tank like this. So the fuel vent can go into the surge tank, and at the same time, the fuel surge tank has a vent on it. And normally there's not fuel in there. But if a little bit of fuel makes its way through here, this has a port near the bottom with a check valve in it, right? Where fuel can travel from right to left here, back into the main tank, but it can't normally travel out to the surge tank. Okay. So we've got some vent lines, but the vent lines off the main tank don't actually vent directly outside. They vent through the surge tank in order to prevent fuel from being able to dump overboard. Okay. It also will, if the plane were to roll a little bit, if some fuel does spill in there, you might get a low level of fuel that spills over, but that fuel will drain back before it builds up enough that it can go out the vent. Okay. So in like a roll type situation. So some of the components, drain valves were there, check valves, flat valves. We saw those that help move the fuel inboard to the collector tanks here in the center. But then our float vent that allows extra air to vent out to the surge tank. Pressure relief valves in case it gets too high. They can also prevent negative pressure. We don't ever want a vacuum to pull in there. So I've just got a few things labeled here. So main tank, the collector tank, there's the surge tank. So when you're reviewing your slides, if you're trying to remember what's what, you should be able to kind of see that and how the venting systems connect those different areas. So vents, anything that's venting is typically going to be near the physical top of the tank. Anything that's like these different flow control, like check valves, those, the red squares and orange circles, those are going to be near the physical bottom of the tank to control the movement of fuel. Okay. If we look at what these look like on the inside, so those air scoops I was talking about, there's one shown here. To be able to connect our vents, we often have a NACA scoop. Who's heard of a NACA scoop before? What is the advantage of a NACA scoop? Don't get debris? Why don't we just put a regular scoop on the bottom of a wing? So the key is the laminar. It doesn't create the drag or the turbulence that a scoop that would stick out. So a NACA scoop is recessed up into a surface versus a typical air scoop that sticks out. Okay, so this recessed scoop, this would be the front of the plane. The air is going to be flowing, from the top down. It is going to allow a certain amount of air to ram into that vent port. So the tanks, actually, when I say they aren't pressurized, they're not pressurized in the typical sense of the word, but when the plane is flying, that ram air force going into the scoop here will provide a small amount of positive pressure on the top surface of the fuel, right? It will slightly pressurize the air that's in the fuel, or that's in the fuel tank, above the fuel, okay? Any ideas why we want a slight bit of head pressure on that? What advantages? There's a couple advantages that'll have by doing that. So yes, in a way, preventing vapor lock in a way. More how's it gonna help prevent vapor lock? Positive pressure to the fuel line. So it's gonna be kind of helping to push fuel into the pump, right? It's gonna assist the pump by putting a little bit of head pressure on the fuel, right? So that's one way, it's one advantage. What else does that higher pressure, is it gonna, think about something it might prevent? It's not really gonna do much with ice. No. So that slight pressure is gonna help prevent the fuel from vaporizing. Okay? It also is gonna help prevent from vaporizing. Why is fuel vapor a bad thing? Fuel vapor can become explosive. So we want the fuel to stay in liquid form. Jet fuel is relatively safe in liquid form. Jet fuel does not burn, per se, in liquid form. We have to atomize it and vaporize it to get it to a point where it's going to burn. So by maintaining some of that positive pressure, you won't get that coming off of it. And then it also, like we said, helps move the air to the thing. So we've got these NACA scoops, and this one just vents directly into the surge tank. Some of them would be connected to the various vent lines off the back of this. Okay, here's a couple other ones. So this is the leading edge up here, trailing edge. Because a lot of students don't realize what they are, but if you want to see one, there's one out on the wingtip of the 727 out there. Okay. They're on the nose of the Seminoles. I think, aren't those ones part of the ventilation system or for the cabin heater or something like that? Yeah, there's ones that help, that feed air for the fuel-fired heater on the Seminoles. Barron has one on the. They have several on the engine cowls for like the turbocharger or like the alternate air, I think, or something like that. So, but the key, the reason they're recessed like that instead of sticking out is that they have less drag and they create less turbulence than a scoop that would stick out into the airframe. But for our purposes, that little bit of ram air there that's going into those scoops is going to help to put some positive pressure into the fuel tanks. Okay. Some of the other ones, things like positive and our over-under pressure relief valve. This one at the top this is a fuel panel. These were the panels, speaking of, that I was talking about on the 727 right here. If you open these oval panels on the bottom of the wing, those are the access panels into the fuel tanks. You know, right on the other side of those panels is fuel. They show some here as well. Okay. So oftentimes, items like air scoops, valves, and things like that are going to be built into the panels. That way, if we have to change one or fix one, it's a lot easier to do. You know, we can remove that panel, and oftentimes we'll have a spare panel, especially in an airline situation, where you'll have a spare panel with that device already ready to go. You can swap it out, and then you can go deal with fixing the failed valve or whatever it might be. So they make them line replaceable, rather than having to go into the tank and then unbolt something else from inside the tank. So here are a few. This is like what a typical panel is showing. They're showing here. It's a flat metal panel. They usually have some ribs in them to stiffen them. Captive nut plates, so they're sealed, and there's the seals that go on these things are kind of cool. I wish I could get one. The seals they usually use a rubber O-ring, but then they also have it's like a jelly rubber, like a jelly steel that has almost like a window screen embedded in it. So when you clamp it down, that window screen creates a current path or a bonding path between the panel and the airframe. But here's one that has an overpressure relief disc, burst disc. So it's just a standpipe, and if the pressure gets too high, it can break this frangible disc. It's a metal disc with basically score marks in it. That would help to prevent something like what I talked about with the Air France Concorde crash. if you got that pressure surge, rather than surging and blowing out just a piece of the metallic structure, it could blow out this overpressure relief disc. And it would be in an area where if it did blow it out and fuel came out of it, it wasn't going to dump it right into the exhaust stream like what happened to the Concorde. Okay? Yeah, it's designed to break here rather than somewhere else. Negative pressure relief valve, this is a big poppet check valve that if the pressure in the wing gets below the pressure outside the aircraft, it's going to allow air to suck in. Okay, that valve will pop open, that air going in, will take the place. Positive pressure relief valve has a standpipe so it can get above the fuel. This one is usually below the fuel. If it sucks air in, the fuel isn't going out at the same time. It might drip a little bit, but mostly it's going to be pulling air in, so it doesn't have to be on a standpipe. Positive pressure is if the pressure inside the wing gets too high. It's a poppet valve that can open. We want it to be located above the fuel most of the time, so that it can vent air rather than fuel if the pressure gets too high. Okay. Looking at these, this is just known as a pressure relief valve. In this case, it provides over and under pressure relief. So it's not uncommon for these two right here, negative and positive pressure relief, to be combined into a single valve that looks like this. So you can actually push up on it. That's what would happen if you have an under pressure situation. They can also oftentimes be pulled down in a positive pressure. So essentially, it's a valve that's normally sealed. It can move either direction. It's almost like a check valve with some resistance, but it can be forced either direction depending on if there's too much pressure, positive or negative on it. So these are commonly, and you can see here, it's another one that is installed in one of the fuel access panels so that it's easier to perform maintenance on it, rather than having to open an access panel and then go find it in another part of the wing body. And here, this one opens at 3 psi. So if the wing gets negative or positive 3 psi, it's going to pop open either direction. Next thing we're going to look at is quantity indication. So we've looked at storage and we've looked at venting. We've looked at refueling and defueling. Now we need to know how much fuel we have. And transport aircraft almost exclusively use a capacitance-based fuel sensing system. Okay. How does a capacitor work? So here's a fuel quantity indication system. You can see we've got a couple capacitors here, and those are the real heart of the system. So how does a capacitor work? It stores energy, okay. What else does it do? It discharges, okay. What else? Tell me, how does capacitance work? What is a capacitor made up of? You got two plates, okay, two plates, right? One's anodic, one's cathodic, two plates. What's between the two plates? Oh, that's a battery, is electrolyte. What goes between the two plates in a capacitor? What? Not a diode. You don't remember? No? No? No, this is basic electrical. Air, what's air? Yes, yes, yes. It can be air. It can be a fluid. Some kind of a non-conductive, typically. Right? An insulator, you got two plates that are isolated from each other. But what's that? So you've got two plates and you've got some kind of a dielectric compound between them. Okay? And so what happens is that the the capacitance will change on a capacitor. Depending on what's between those two plates, it will change. So in a fuel system, if you look at this diagram, what can be between the two plates? Fuel or air or somewhere in between. Okay? So as that fuel changes, as that fuel moves inside of that capacitor, it changes the dielectric constant, and it's going to change the capacitance of that sensor. That sensor is a capacitor, but it's a variable capacitor. And it varies with the level of fuel, the ratio of fuel versus air that's between the two plates that make up the capacitor. Okay? So typically what we see is something that looks more like this. Okay? We're going to have multiple capacitors that serve as our tank probe. Now, how are those all connected? They're in parallel. When you have multiple capacitors connected in parallel, what do they function as? Well, multiple capacitors in parallel, they basically function as one giant capacitor. Okay? And so, as this fuel were to move between these, the total capacitance of this kind of bank right here at the top of fuel tank probes is going to change. So you're then going to compare it. You need to know how that fuel affects the capacitor. So you're going to have one that's called a reference capacitor. It's at the very bottom of the tank that you want always immersed in fuel. And that way it gives you a reference for what the dielectric constant of that fuel is. Because it could be, Jet A versus Jet A1 versus JP8. They can be all slightly different. And they're all going to result in a slightly different change in capacitance. So you have to have a reference capacitor in order to do that. And then some also have a densitometer. Why would we need a densitometer? What's a densitometer going to do? Going to tell us the density. Why do we need to know density of the fuel? We're going to change our flow rate. What is this level that the fuel tank probes, what's that going to give us? Is it going to give us so what do we measure fuel in on transport aircraft? We use weight. In the United States, we use pounds. The rest of the world, we use kilograms, right? Does the level in here directly indicate the weight of the fuel? It's going to give us volume. So a densitometer gives us how many pounds per gallon or how many kilograms per gallon. And so our fuel system can then convert a volume to a weight. Even though we can't measure the weight, we can't use a scale to weigh the aircraft or weigh the fuel tank. Okay? And not only that, the densitometer, the density of the fuel can also change based on temperature. Warmer days, the fuel is going to be less dense than cooler days. So, on a warm day, 100 pounds of fuel is going to take up more space than on a cool day. Or on the ground, when the aircraft is warm, the fuel is going to it's going to be less dense than when it's flying at altitude at negative 40 degrees. So the fuel quantity system is going to have some kind of an indicator computer with indicators. We're going to have our capacitance probes. We're going to have a reference capacitor, which is basically another capacitance probe, fuel level probe. A densitometer, okay? Most nowadays have something called a compensator, which basically is kind of the combination of a reference capacitor and a densitometer together, okay? And then we also have things like high and low level sensors to make sure we don't overfill the tank and to give us a warning if it gets too low. So here's a kind of like I said, the newest aircraft, this densitometer and this reference capacitor are going to be combined together into a single item called a compensator. It's going to compensate for changes in the fuel, which could be changes in density, changes in dielectric constant, all that kind of thing. Okay? So if we look at a map of a fuel system, here's a tank, and you can see tank unit, what they call a tank unit here. There are 13 of them. Those are the fuel level probes. You can see they're all over in the aircraft, and they're going to be working essentially in parallel with one another. Older aircraft, they were actually wired in parallel. Newer aircraft, each probe is wired back to a computer on its own. The computer looks at them holistically, But by being individually wired back to the computer, if one fails, it's really easy to find. The computer will tell you that left wing, say probe number 10 has failed, right? Back in the day when they were all in parallel, your computer would say left wing, something's wrong. And now you've got to disconnect the probes from each other and figure out which one is causing the problem. Okay, so today they're all kind of run back. But you can see our number 1 probe, which is at the lowest inboard point of the tank, also has that compensator on it in order to figure out density and reference capacitance. Okay? There's a low-level sensor right here. If this sensor no longer senses fuel, lots of red warnings come on. Because that's the last one before, the pump's not going to be able to pick up fuel anymore. Okay? And then this one's also has a fuel temperature sensor in it. What they don't show here is the high-level sensor. On this aircraft, they consider the high-level sensor part of the fueling system rather than part of the fuel quantity indication. And that is, if fuel hits this high-level sensor that would be out here, it automatically closes the fueling valve so you don't dump a bunch of fuel on the ground when you overfill the fuel tank. Okay. The other thing they have here are magnetic level indicators, these triangles. And we'll look at those in a minute, but those are to be able to figure out what the fuel level is if the electronic system fails. So the actual probes look something like this. They're basically long cylinders. They have an inner set of plates and outer. So you've got a tube with a couple of capacitance plates in it, and fuel can flow inside of here. And fuel acts as your dielectric between the two plates. The plates should not touch each other. They're held in a way that the tubes that they can't touch each other. But the fuel is able to flow up and down in them. Okay? And then these are all wired together, and again, they act like one big capacitor throughout the whole tank. They don't even have to be measured vertically or mounted vertically. Old style ones had this big end on them where they would bolt into the top of the tank or the bottom of the tank. Some bolted in from the bottom, some bolted in the top. But new ones can actually be inside the tank, and they look something like this. And you can see that one's a little too tall to put vertical, so they just move it sideways a little bit. The advantage to that is you don't have to have 20 different size sticks. You can put them slightly sideways, and the fuel's still going to go up and down, right? Halfway up, halfway down. Part way up, part way down. So you can see there's some big, the wing root, as you get out to the wing tip, right? It's showing where B is. There's all those 13, actually I should say 12 sensors. There's 13 total. One of them though, C, the one right here, is shown over here on the right. That has the compensator at the very bottom of it. It's another, if you look closely, there's another pair of plates here. So you got a pair of plates in here for doing level sensing. You've got another pair of plates here that should always be immersed in fuel, and that's your reference capacitor. And then it also has a densitometer built into it to do both jobs. And in this case, it happens to also be integrated with the number 1 inboard fuel sensor. Right? They're all in one package there. So here's what I was talking about where they're wired individually. So here's that, your probe number 1 and the compensator get wired back, compensator, probe 1. You can see they've got a common kind of ground going to them. And then all your different sensors, and by wiring them all back to they call it a fuel conditioning unit. It's basically a fuel computer. By wiring them back individually like that, we are able to, if we have a failure of a single sensor, we're able to pinpoint it very easily, because that fuel conditioning unit will then also be integrated into the indication system. And so whether it shows up on ICAS, you'd probably get, for the crew, they'd probably get like a fuel quantity indicating system fault. You could go into a maintenance function on that ICAS computer, and you could actually pinpoint which specific sensor probe is causing the problem. Okay. I'm going to show what the densitometers look like, and then we'll call it a day. So there's 2 types of densitometers. Okay. Older ones are what's called a rotational type, and that's what's shown here. You can see it has a little paddle wheel on the end, okay? Newer ones are a piezoelectric type, and these can be torsional or longitudinal. So the rotational one that I have here, essentially what it is a motor that drives a little paddle wheel. Okay. That's immersed in fuel. And when you try to drive that motor, as the density of the fuel increases, it'll take more power to spin that wheel. As the density of fuel decreases, it'll take less power to spin that little paddle wheel around. So it can judge the density based on how hard it has to work to spin that little paddle wheel at the end. Okay. Piezoelectric is your more modern ones. Essentially what you have is two piezoelectric crystals. What does a piezoelectric crystal do? What do we do? Okay, so pressure generates electricity. That's what's happening down here, or vibration, which is a changing pressure. You can also put a known AC signal in, and it will generate some kind of a physical movement, a physical vibration. So it's two dissimilar materials. Often they're like a silicone and can't remember what else they use. Most of them are like a silicone oxide type piezoelectric. So we put a known AC signal in. It vibrates like a wire, a connecting element. And then you have a second piezoelectric sensor that's sensing the frequency of the vibration coming out of that element. And again, if we have it in fuel, the more dense the fuel is, the more it's going to damp that vibration, and it's going to change the AC out signal. It'll either change the frequency or it'll reduce the amplitude of the fuel coming out, right? The more dense fuel is going to slow it down, and it's going to reduce the amplitude of the outcoming signal. Less dense fuel, it's not going to damp the signal as much. So the amplitude will be higher, frequency will be higher. And so it can monitor what the fuel density is based on that change in AC signal from the signal going in to the signal coming out. The other part of those are the paddle style. So I also said there's torsional rather than longitudinal. Torsional is we put in that known AC signal, and rather than doing a linear wire, it's got that same kind of paddle wheel, but then rather than trying to spin, it's trying to vibrate the paddle wheel side to side. And then it's seeing what the output vibration is from that paddle wheel. Because again, the more dense it is, the more it's going to damp the movement of that little paddle wheel trying to go side to side. And these are, anything modern is going to pretty much use a piezoelectric one of these rather than the little motor. The old school ones where it had a little paddle wheel that spun with a motor, those motors were a high failure item. They were, versus these are a solid state item. Solid state items tend to have much better reliability. There's no moving parts. It's just sitting there having to vibrate a little bit. Okay. So I'm going to go ahead and stop there.